In the following tutorials, we will discuss how to control robotic hands. This will be useful for our final dexterous manipulation challenge, performing pick and place, and even more complex manipulation tasks. To do so, we will first introduce some sensing methodologies. After that, we will discuss 3 control techniques. At the end of this tutorial, we will analyze what challenges you might encounter on your path. But first, what is the control in the field of robotics? When we refer to control, we usually refer to controlling the states of the robot. For example, the position of the robot itself, its velocity, the forces it applies to the world, or even the temperatures that are acting in our controller electronics. So to control a robot, we first need to calculate the state we want a robot to achieve. We will call that the reference or the desired state. The signal has to be applied to the system, which is the controller and the plant. The system has to be designed in such a way that for a time t equals infinity, the robot should assume the reference pose. However, there are some issues with this example. What if the controller is not performing well? What if the model of the plant is not accurate enough? So the system might converge to a wrong final state. To solve this issue, we can measure the actual state of the system, and instead of giving the controller the reference state, we give it the difference between the reference and the actual state. This is a closed-loop configuration. For this reason, sensing is quite fundamental for reasonably good control. So how can we sense the position of the root of the robotic hand, the position and orientation of the fingertips, and the forces that we are imposing on the environment once the hand touches, let's say, a table or an object? When you want to sense the pose of the fingertips and the links in your gripper, you have basically 2 options. You can either directly estimate the position of the fingertips and the joints with respect to the world frame, or you can indirectly do it. For example, you compute the relative position to the wrists, and from that state of the wrist, you then can actually compute the absolute position of the finger. So for the first approach, we can place, let's say, infrared refractive spheres on suitably spaced locations along the finger. With an infrared camera, we can then easily find those balls in the picture. There are algorithms that allow for 3D triangulation using a stereo vision setup. All of these combined together can then extrapolate the position of each joint in the world frame. So for the second solution, we only need to know the angle between 2 lengths. Last lecture, we talked about transformation matrices that transform the relative position of an object between 2 frames. The robotic arm always knows where the anti-factor is located. You build your own design so you know the lengths of the wrist attachment, the palm, and also of the fingers. So all of these aspects here. If we were able to know the orientation of each element, we could use the transformation matrices to obtain the fingertips positions. Some of the techniques to measure the orientation of the joints are: you could measure with a motor encoder the angle of the motor shaft. You could use flex or stretch sensors to measure the relative bending between links. You could even use inertial measurement units, or it's just simply called IMUs, to provide an absolute orientation relative to a world frame. Or you could even look for other sensing principles. The actuators we use have an encoder that knows, within a certain range of accuracy, the current angle of the rotor with respect to the stator. The motor's rotor is attached to a spool on which we wrap up the tendons. Since you know the diameter of that spool, you can retrieve from the encoder the length of the unwrapped tendon. After some math, you will see that this angle of one link relative to the other can be found out this way. Unfortunately, this option is not that ideal. The reason for that is that the compliance of the tendons and the types of the joints that you use will potentially provide some troubles. A pin joint is pretty much ideal for this setup, but if you use a rolling contact joint design, it could introduce an error that can substantially grow up to, let's say, even 30 degrees or more. We should then look for a modified visual sensor modality, so not just a plain old encoder, or go for even completely other solutions. So this flexible sensor board consists of a thin layer of capacitors and resistors. After you mount this board on the finger, it senses the rotation of the joints. Knowing where we place the sensor, we can then roughly estimate the relative amount of rotation between each link. These sensors also come with some limitations, since they require additional readout electronics, and they also add some resistance in terms of force that acts around the joint. Whenever you try to pull on it, you have to overcome that additional resistance. These inertial measurements units, or IMUs, are rather small and fairly easy to use pieces of electronics. They can actually measure the acceleration and the absolute orientation of an object. They can be fairly small, but are not always reliably depending on the setting and the use case that you have in mind. So IMUs accumulate noise and they need to be calibrated again after some time. Nonetheless, we will need one IMU for each link to be able to reconstruct the actual fingertip position. So a powerful tool that you can use is a Kalman filter. Kalman filters are particularly useful for measuring indirectly, or one might say predicting something that cannot be directly measured otherwise. In the setup here shown on the slide, we can measure the length of the tendons when we only know the angle of the spool that is connected to the motor. So we can define as x what we are trying to predict. That could be the tendon length. And then we define as z what we are actually measuring. That could be the encoder's output. Now the idea behind this arrangement is basically to create a closed-loop controller that can receive c and try to predict x. The controller at the hand should also know a suitably accurate model of the system. And this way, the Kalman filter can be updated with each iteration, predicting at each step an even closer estimate of the real value of interest. So this is how the loop plays out. In step 0, we initialize the estimator with the best initial guess about the state x that we want to predict. In step 1, we read from the sensor the value of z. Next, the filter can estimate the current value of x thanks to a particular equation called the update equation. This function tries to estimate the current state exploiting the past measurement. A simple example of that can be the mathematical average value. And even more advanced variations of the Kalman filter, they implement uncertainty, or they give weights to the measurements in proportion to when they were measured. And there are more options to that. So after this, we can now output that predicted state x, and with the system's dynamic model, we can predict the next state of the system from the current state. In the final step, we exploit the closed-loop structure to feed the update equation with a new measurement and the current predicted state. Now this whole cycle repeats. Well, Kalman filters exist in a variety of versions, and their mathematical proofs could take up many lectures. Therefore, that actually exceeds the scope of this class. So if you're really interested in this topic, you should check out classes such as recursive estimation. I will leave a useful tutorial in the description of this video. You can go there and check it out yourself. Many other solutions can be found, so feel free to explore new methods with your colleagues while you're working on your project. This year, we did not provide you with any specific material for sensing in your robotic hands. You can either purchase a sensor with your extra allocated budget, or you first focus on the option 1, which was to sense the motor positions using an encoder. Well, next up, we will discuss touch sensors, and that's in particular force sensing resistors and tactile skins. So both these solutions use a special resistor setup that changes its resistance when a force is applied. There are also variations where instead of using a resistance, you can use a capacitor instead, and you just measure the change in capacitance. In the first example, only one resistor is added to the fingertip. It only measures one-dimensional force that's applied on the surface within a certain intensity range. The second example, that's still in development at ETH Zürich. Here, the core idea is, why should we limit ourselves to just one dimension? Can we not make the whole setup so small and multiply it that we can make thin layers where we have many of these sensing units as an array? Therefore, we create a tactile skin. So maybe one day we will be able to cover the whole silicone skin of our robotic hand with such an artificial skin. In the first part, we saw how the estimate of the pose of the fingers is done in real time. One family of solutions is more direct, while the second family requires a bit more of math. Lastly, we saw two methods to compute the forces applied to the robot. Remember that this is useful for control if we can estimate the real state of the robot, and then we can create a closed-loop controller. Now, that's what we were going to discuss in the next part. Alright, let's now dive deeper into the realm of robot control. In the past tutorial, we talked about different models of robotic systems. We understood that we could create a dynamic model that only cares about positions and velocities of the fingertips x, w, and the joints q and q dot. So we can write a dynamic model that takes into account forces, frictions, and inertia, and other effects. In this unit, we will discuss how to do position control, reference tracking, and dynamic control with a final introduction to visual control. When controlling the position of our robot, the easiest thing will be to exploit the inverse kinematics. So when building a forward kinematics model, we arrive at this equation that was learned hopefully in the past units. Well, now we can actually invert this equation and obtain a formula that tells us what q dot is. And we can also write that in a differential form, as you see here in the last line on the left side. Here, you might face to start some under-actuation problems in this case. And since each finger can be approximated as a 2D planar robot, if you now choose a 5-finger configuration, you will have exactly 2 actuators to move the fingertip in 2 dimensions. If you choose to have more joints, you will have to remember that some of them are dependent on each other. So if you find yourself with a square invertible matrix J, which is the Jacobian, then the inverse of the Jacobian will have just one unique solution. But notice that this is not always the case. A matrix can be singular and not squared. And in those cases, you will need a pseudo-inverse, usually indicated with a cross at the apex. Or you solve an optimization problem to find a solution for this. Independently on how you obtained the inverse kinematics model, you almost have all the ingredients necessary to execute the inverse kinematics algorithm. So with the solution from the inverse kinematics, you can apply a closed-loop system control to get the anti-effector into the desired configuration. You will only need a desired anti-effector position, and then the control loop will give us the required joint positions. So here you see an exemplary control loop used for inverse kinematics based control, and it's using a Jacobian, as you can see. So now let's talk about trajectory control. So in this case, we have a desired position and velocity of the anti-effectors. That means the fingertips. And now we want to know the speed of the joints to obtain such a configuration. The solution is similar to the one we just talked about. We need to add a component for the velocities in the reference and define a closed-loop controller. So you have to remember that the reference is what we call the state that we want our robot to match as well as possible. So to code this up, we need to choose a value for k, which represents the position convergence rate, and apply a convergence algorithm like the one we saw before at each time step t. Well, nonetheless, the motors we are using can be controlled in position, in torque, and in speed, so both methods are actually a valid approach. So here you see an exemplary control loop used for trajectory control. So what if we know much more about the system at hand? We know the weight of each link, the payload we are carrying, and the additional external forces that are at play. In this case, we can exploit a dynamic model. With a dynamic model, we can explicitly write down the desired forces to apply on each finger to the surface. This allows complex grasping configurations with 1, 2, 3, or even more fingers that are in contact at the same time. So now we know already what our desired configuration Q is and also what its derivative is. These are the inputs to our system. Now you have this dynamic model. You see Q and Q dot and Q double dot in there. If we know what the desired generalized acceleration shall be, then we can also write the following equation, Q double dot star. And it's a formula that has a proportional coefficient and also a derivative-based coefficient. Now, the joint torques can then be computed as you see in the last line, where the tau star is a sum of an inertial effect and the remaining effects of the dynamics. In this last section, we chose our desired state of the control loop to be the states of the motors. That was Q, Q dot, and Q double dot. Well, in real-life applications, though, it's far more easy to have a desired state of, let's say, the antefactor. So imagine you are building a robot that is in charge of your house cleaning on a daily basis. Well, I don't want to say that you are one of the messy type, but we always, all of us, leave something behind. So wouldn't it be nice to have a robot clean up after us? So let's imagine you're leaving the house to go grocery shopping, but the bottle of orange juice is still outside the fridge. Well, thanks to a deep learning vision algorithm that you created, the robot can now actually triangulate the position of this orange juice bottle with regards to the world frame. And that's thanks to the algorithms that we will discuss now. We can actually translate our robot antefactor towards that position of the orange bottle. How can you now control the antefactor pose or the velocity from a more dynamic point of view is the question. All right, so remember that we have this equation that maps the Jacobian and the derivative of the configuration space, so Q dot, towards chi E, which is describing how your antefactor is located. So now, this is actually called a task space formulation. And here we have the accelerations and also the velocities and positions of the antefactor. And there's also the force Fe that will show up in a moment. That's actually the total force at the antefactor. So now you take this first line you see on the slide and you derive it with respect to time. Here you have to make sure that you also then keep track of the derivative of the Jacobian. And now if you solve the dynamics equation for the joint acceleration and substitute into the equation above, what then we get is a version for chi E dot. And that is now in regards to the dynamics. Now, remembering the relationship between tau, which is the forces, or let's say the torques on the motors, and the Fe, so this total force I just mentioned, we can now write the full task space formulation that you need for control. And for completeness, I show you on the slide the formulas down on the right. So knowing the relation that we just introduced, you can implement the controller by calculating chi E dot star from the other values that you see here on the slide. This way you are ready to go and can use task-based control. So what have we learned so far? There are a variety of methods that a robotic engineer can use to control a robotic system. Each one of those has different inputs and outputs, but they all serve the same purpose of getting the system as close to the reference as possible. The majority of these methods are nowadays already implemented in the simulators and control libraries. Nonetheless, they are of fundamental relevance for the topics that are ahead of us. So remember that we don't really implement sensing at the joints. This means that we can't really know the real position of the fingertips nor of the joints, but only use the encoder information and make an estimate from that point on. All right, remember we talked about simulation and modeling. Simulators are great, but, well, they don't cover everything that you actually have going on in the real world. It's not only that simulators are too optimistic in their calculations, but even things such as tendons, actuators, or even the soft skin that is over your robotic hands, all of these have a lot of challenges hiding there in plain sight. Obviously, these challenges don't mean it's impossible. It means that Smart engineers like you can just come up with suitable solutions for them. So now the question is, what are the problems that we might face and how can we solve them? Well, there's uncertainty and partial observability. There's a long horizon problem. There's under and over actuation, the stim to real gap, the tendon strain, the skin's non-linearity, and the encoder's sensibility. So what does that mean? And what are some examples? And what are potential solutions? All right, let's start with uncertainty and partial observability. What if you don't know what the world looks like? What if we don't know the weight of the cup that our robotic hand is supposed to grab? What if the cup contains liquid? We can't just pick it up the same way as if it was empty. What if the world is changing while we are doing the task? We need to accumulate information before we are acting. So, for example, we are using our robotic hand to help our grandparents to clean the dishes and glasses in the kitchen after lunch is over. First, the robot will grab an empty glass. Probably the glass's outer layer will be clean. So the robot has to apply a force to the surface that depends on the friction between the silicone rubber and the clean glass. Then the robot will rinse the glass in water, and there's also some soap in there. Everything will become obviously more slippery. So the robot should be aware of the changes in the friction coefficient and accordingly compute different contact forces and basically adapt its behavior to this changed scenario. So for this type of problems, here comes the power of reinforcement learning. What can be done to overcome this issue is to train your robot with more and more cases, different possibilities, complete randomness. The more the differences in your challenges, the more you randomize them, even to slightly go off from where the sort of planned track is, the more robust the final policy that you're learning will actually become. So hopefully this cleaning the soapy glass challenge will be one of your training scenarios and the robotic hand will be prepared for it. Let's get to the long horizon problem. So making plans into the future makes control hard. Maybe the robot started to do an action that requires a long time to be completed. But the prediction horizon, that means the horizon in which the robot can see and predict what will happen next, is shorter than the task duration. So for example, you are in an autonomous car and the system can only see 100 meters ahead from where you are into the space in front of you. So this means that it can only predict its trajectory up to 100 meters since it doesn't know what is beyond that distance. You might think that 100 meters is a safe distance, but you're on a highway going 130 kilometers per hour. And suddenly your LiDAR, which is the sensor you're using to measure obstacles, sees something ahead of you and the algorithm will tell it to instantly start braking. Your braking distance is 99 meters. Well, another example would be a humanoid robot that is doing a backflip. In the middle of the jump, something goes wrong and you can't do anything about it. So in these scenarios, the trivial solution, if possible, is to get a longer horizon. This comes with the trade-off of efficiency of the algorithm. If we have a longer horizon, the computations will take longer. Therefore, we can't keep the same update rate as we did before. Otherwise, one can try to operate with a certain range of safeness, so that if the unpredictable situation occurs, meaning something comes just up in front of you, the robot has a way to stay still within a safe regime. You can make this for the worst case scenario or for the more common unpredictable scenario. The choice is completely yours. Similar to this example, we have also under-actuation. And it is not so similar with the other brother of under-actuation, which is over-actuation. So under-actuation can be recognized as a setup where the degrees of freedom the robot has are not enough to execute an action. Think about our robotic fingers. If we use only 2 actuators, we can easily position the fingertip everywhere in the 2-dimensional space. But what if we want to position the finger in a particular point in space with a defined orientation? With 2 degrees of freedom, we can solve a task that has 3 independent requests. 2 for the position, x and y, and 1 for the inclination, that means the angle. So over-actuation is the opposite problem. The robot can satisfy a request with infinitely many solutions, and therefore it doesn't know which one to choose. Can you make an example of over-actuation with 2 degrees of freedom for a robotic finger? So for over and under actuation, the solutions are different. Both make the inverse of the Jacobian in the inverse kinematics impossible to compute. The solution is to use the pseudo-inverse, which is a particular matrix that best generalizes the inverse matrix for non-square matrices, which is in this case the Jacobian J, having not an n by n form. So now, the sim to real gap. Sometimes, if you do the same test in the simulator and in the real world, the outcome will be drastically different. Even the best of the simulators can, from time to time, fail to be faithful enough. This can happen if we mistakenly evaluated some friction coefficients or softness, if we neglected nonlinearities, or all the other assumptions that we made in simulations. The solutions to this issue are many. One is domain randomizations. You domain your model for more and more scenarios to get it ready and be more robust. You can do behavior cloning. So you look at the movement of an expert doing the task and you try to copy it as a reference. And therefore, the robot is trying to emulate that expert as good as possible. And you also could use something called residual learning. Another big problem you will face during the workshop is the tendon problem. If you remember, we assumed that the tendons should be perfectly non-elastic, so they shouldn't really strain. So any force that's applied, this thing will not change its length. However, you will see that the tendons do stretch slightly. And this is a big issue for our sensing system that totally relies on the fact that those tendons should be ideal, meaning they should not stretch. So the strain of the tendons and the nonlinearity of the soft skin both have a similar yet simple solution. If you know the real nature of the nonlinearity and it doesn't influence much on the computational requirement of the system, you can try to implement it in simulation. Otherwise, take into account the fact that they are not ideal, these tendons, and just slightly refine your controller to deal with it. For example, you could add a small bias to the actuator so that the tendons are pulled a little bit more than planned. So there's also soft materials, and they're quite non-linear. And your whole robotic fingers will, at least to some extent, be covered with silicon rubber. In a previous tutorial, we briefly talked about softness. We talked about the per-source ratio, and we could have gone in much more greater detail about hyperelasticity and these nonlinear effects. However, these will be discussed in next semester's soft and biohybrid robotics class. So for now, the takeaway should be, you might have some trouble if you simply assume your robot to be a hard robot, but you have to deal with soft tendons, soft skin and other materials that are acting onto your structure. You need to model them. Finally, there are encoders. The motors mount encoders with a fixed sensibility. They can estimate the rotation of the rotor only up to a certain gap. This also means that you can only estimate the length of the tendon to a certain degree. The solution we are using for sensing with the encoder is not at all ideal. Since we cannot directly estimate the pulling and pushing of the tendons, we can use a Kalman filter. Those are particular types of filters that make a prediction of an unobservable variable using the sensing of an observable variable. So those that we just discussed are only some hints for a solution. They are more than enough for the issues you will find in this course, but I also meant to inspire you to do more research on this topic, if you find that they are necessary as you're going along in your challenge. So next up will be how you can use computer vision to help in the manipulation task. So today we talked about sensing. We described a few methods to estimate the position of the fingertips and the joints, as well as sensing the force applied to the world by using your robotic gripper. Secondly, we discussed many control methods, both in the joint space as well as in the task space. Finally, we cited a few challenges that you might have to overcome during the design of your controllers. Up next, in the following tutorials, we will dive deeper into teleoperation and reinforcement learning algorithms.